right. Where were we last time? We saw the coding theorem. Let us just get back into the bath. For all x and y, k of x given y is equal to minus log of p of x given y plus O of 1. Awesome. So one of the relation was quite clear. The harder side was to show this part, and we spent the whole period on it last time. I finished with a few remarks saying that the proof is not completely over. Right? And what were those? One of them was that we were allocating, okay, so what was the idea of the proof? We were building a very large tree in which we were sort of putting each possible string to be produced on some node. And then the program was becoming the address of the node to get there. And we wanted the shortest address possible. So we were computing the tree for all strings until we reached the desired address. So we're saying, for example, our string x is going to be at address given by, in the example, it was 0010. Now there was just one remark, and it also explains why we have this plus one. We were allocating a node at level the ceiling minus the ceiling of log p of x plus 1. We were going one bit further, and we could have asked why this plus 1. So we should verify that this way of allocating strings to nodes in the binary tree will never run out of space. Okay, why? Again, we're going to be using Kraft inequality. Sum over all j's such that aj is not nothing. You know, like aj was the fourth entry in our quadruples, and sometimes it was given nothing. It was giving nothing when the leading bit of the lower semi-computation of p of x was not changing. But every time it was not nothing, aj was a non-trivial node, the address of a node in the binary tree. So I'm subbing over all the non-trivial nodes on the binary tree, 2 to the minus the length of aj. And I would want this quantity to remain smaller than 1. If it remains smaller than 1, by Kraft inequality, it means that these numbers, the length of aj's, are valid length. In fact, you know, I'll never run out of space in my binary tree. Here. I could then interpret the AJs to be a prefix-free set of code words, which by construction it is. Because every time we assign an AJ, we cut the branch of the tree. But if this is smaller than 1, we're fine. So let me just rewrite the sum as the sum over all x and the sum over all j's, such that AJ is not the empty set and xj is equal to x. Okay, because AJ is, so far this sum is, I'm summing over all assignments of AJ, and now I'm breaking that into pieces. You know, there's going to be infinitely many AJs, which are no. Only finitely many AJs will be assigned to a given x, but all string x will have some, that's what I want to say, all string x will have some AJs associated to it. In the best case, there will be only one, but it doesn't matter. So I'm breaking the sum this way. 2 to the minus length of AJ. And then this is smaller to then sum over all x. And then what am I going to, let me write it down. 2 to the minus ceiling minus log of p of x plus 1 plus 2 to the minus ceiling minus log of p of x plus 2 plus 2 to the minus ceiling minus log of p of x plus 3. I am not closing my parentheses. Yeah. Plus dot dot dot. Okay. Why? If we remember in our example, what did we have? We assigned some node at depth 6. And eventually we assigned some node at depth, at depth 4. And depth 4 was this smallest possible depth because we were reaching the minus log p of x. So the leading digit in the lower semi-computation of p of x could not change anymore. And the plus 1 was, by construction, we had to, so in our example, what did we have? We had s of x5, where x equals 1, 1, 0, 1, 1. This was equal to 0.001, 0, 1, 1, and so on. But we were supposing that the actual p of 11011 was equal to 0.001 1, 0, and then I made stuff up, obviously. Okay. So what we did is we allocated a node, namely it was called A5. The address was of A5. We allocated it to a node at depth 4, given by this expression. This was the last node that we will allocate for that x, because it was the last time that Sx will have changed its leading digit. Having a 1 here, that's a 1 at the 3rd position. The algorithm tells us, okay, reserve a node at length plus 1, so 4. And now, what is...
Can I interrupt for a second?
Please do.
Remind me again, how do we know that that's the last time it will change?
We don't know.
Digit?
We don't know because we don't know p of 11011. But it doesn't matter. So A5, the A5 was, just to recall everything, was 0010. It was the lexicographically first available node in the tree that we constructed. At depth, what is it? Yeah, depth 4, exactly, because of its length. But we got the 4 from the fact that the lower semi-computation of S of x5 had a leading 1 at position 3, so we needed to do +1 to get 4. But just to remind you, we also allocated a node for that string. At A2 was the node 000010. It was a node associated with the same string x, because we found that the second program that halted in our dovetailing of all programs that halt also produced that x, and it was produced by a program of length 5. So our lower semi-computation of Sx was yielding 0.00001 00000. It was the first time we have a program that produced x in our dovetailing of all programs. So by the criterion, we had to assign a non-trivial address, namely A2, to x, and A2 had to be of length 6. So we allocated that. And then in the example, if you recall, we also had another program that produced x, but this time it was a 6-bit long program. So it contributed with this one here, which did not make the leading digit change. And so we didn't attribute, well, A3 was equal to nothing. We moved forward because the leading digit was not changing. Now, the thing is, eventually, the lower semi-computation will stabilize the leading bit of the probability, P of x, and then we will have a program of length 4, namely A5, to generate x from that big tree. That was the idea. Now, yeah, I sort of need to deploy the idea to make sense of this sum. So what am I doing here? If we think of our string x, here I'm summing over all the AJs that actually correspond to x. In our example, we only had 2 AJs that corresponded to x. We had A2 and A5. And because I said, suppose that, the actual value of P of x is this, then it's not going to happen anymore that a leading digit will change. So the lower the huge dovetailing computation will find more programs for x, namely for 11011. It will keep on lower semi-computing Sx, but it will never change the leading digit. But that's fine, that's not a problem. Which I think you asked a similar question last time, Will. You said, when do we know we're done?
Still confused about this. Because, it's fine if I have an oracle that tells me, it will stabilize. I don't know, this is the leading bit of P of this X.
Mm-hmm.
Then I sort of know when I can stop and actually compute this sum. But otherwise, I'm not sure. I have to run forever, and maybe on a very deep layer, the entire layer could all be programs that spit that out, and then there'd be the bits would keep overflowing and rolling upward.
Yeah. But eventually you will find a program which will stabilize the first bit. In my example, I made it easy, so we found a 3-bit long program, which was the reason why we stabilized the third bit like that. But in what you're saying, where you have many, many long programs that together could also happen, that together they cascade and eventually stabilize the first bit. This could also be a way in which it's stabilized. But it will remain that at some point, one program will make this thing stabilize.
Yeah.
And then this thing will stabilize, and our tree will say, oh, I've got a new leading digit. It will not know it's the final one. It will say, I have a new leading digit. Let's assign it a non-trivial node. A1017. And then the reconstruction for x is just the value of A1017. Well, with all this computation.
What do you mean the reconstruction of x?
Oh, so the question was t on some input will have to produce x. And the input, we want the input to be of length, let me call it a. We want a to be of length minus log p of x.
Okay, right.
Plus
The
all.
A's that we're constructing are eventually going to be
The-
prefix code words for a Turing machine that is producing all the strings.
There you go.
Uh-huh.
There you go. And that Turing machine is essentially, doing this massive computation, computing quadruples, until you assign a node 0010. So if I give the input, if I set the input to be 0010, then my huge my Turing machine computes this whole list of quadruples. It lower semi-computes not just p of x, but p of x prime for all x prime to do this calculation. And eventually it goes like, oh, I've got a node assigned at the address 0010. Great. Well, the string corresponding to that node is x.
Okay.
And now output x. This was the idea of the reconstruction. So again, what have we done? We found a Turing machine on an input of size minus log p of x, which produces x. Now there's two arguments to say. Now you can say, well, we invoke the universal Turing machine to simulate that Turing machine. And so we find one program for the universal Turing machine of length log p of x to produce x. Therefore, the shortest program is going to be smaller. That's how we finished last time.
And the universal Turing machine simulation just gets eaten into the O1.
Yes,
It's
exactly.
already there because we needed this program.
Yeah, because exactly t, this large, even though, well, it does a crazy computation, but in terms of program size, it remains constant.
Yeah.
The only non-constant part will be on which node should he stop and produce x. That was the idea. Okay, yeah, we needed to have that conversation to make sense of whatever's going on at this moment. It was a week ago, and it was a hard proof. But now, what am I doing here? I'm looking at all AJs associated to X. There should only be finitely many of them. Like in our example, we had A2 at length 6 and A5 at length 4. They're, but what I'm going to do here is I'm going to upper bound this quantity by assuming that, so this will be my leading term, but I'm assuming that all the other terms will contribute. Like if I'm assigning a 1 to each possible place after place number 3. So it's a sort of a very conservative assumption because I'm adding infinitely many terms, whereas in fact I know that the lower semi-computation of x will have stabilized the leading digit after only a finitely many programs will have been evaluated. So this sum, in fact, well, this sum here should be finite, but I'm upper bounding it worst case by the infinite sum. Okay, at this stage I've got a fun fact number 2. We had fun fact number 1 last time. If I have a number beta, which is in b and b plus 1, like this. Yeah, what did I call them last time? Hard and soft. Yeah. Closed and open. Well then, minus beta. What's minus beta? It's going to be in minus b minus 1. I'm reversing the interval, and b, and this is going to be closed.
Minus B.
Thank you, minus b. And therefore, all this to, we're going to get there. What is the ceiling of minus beta? And then I'm taking, well, we'll do two things. And I'll take the minus again. Well, it's going to be minus, what is the ceiling of that? It's minus b, right? And I'm taking the minus again, so I've got b. So, all this to say that, which is equal to the floor of beta. Okay, it's in this case, it's the floor of beta. So I have, that's precisely what I have. I have minus the ceiling of minus something. Minus the ceiling of minus something. I'll just replace it by the floor of that very thing. So that's equal to sum over x, 2 to the minus, no, there's no minus anymore. Yeah. Log p of x, it's now a ceiling. And, oh yeah, this plus 1 was, I'm going to put it in evidence. So I've got 2 to the minus 1. And then I have 1 plus 1/2 plus 1/4 plus, right? And this is 2. And so this is going to be smaller than sum over x of p of x. Because I take the, if there would be, okay, the 2 cancels this thing here. And so I have the floor, but if it wouldn't be from the floor, then 2 to the log of p of x would just be p of x. But since I take a floor, I have a quantity. In fact, no, I should.
No, it's correct.
It's okay.
Yes.
It's okay?
Yeah.
Explain me why?
To the axis monotone increasing. So it's, if you replace it with something higher, you get something higher.
The floor is more like
Oh, yeah.
it's hard.
Yeah, it's beautiful. It works. Thank you. And this is smaller than 1. So we don't run out of space. This is smaller than 1. Why? From the definition of this, we know that p of x was a, yeah, sum over x of sum over all p, such that u of p equals x, 2 to the minus length of p. Well, I'm summing over a bunch of things which are programs in a prefix-free set of programs. So I'm summing over a prefix-free set, 2 to the minus the length of the prefix of the program. By crafting equality, it's smaller than 1. Okay, so this completes the proof, because now we know that I'm not assigning nodes in any kind of way. I'm assigning nodes in a way that I know I will not run out of space. So this was sort of needed to finish the proof of last time. Are there any questions with that?
Yeah, I think coming back to the earlier discussion of the Turing machine that is running in the O of 1.
Yeah.
Basically, I think the issue is that Turing machine runs forever, right? Like, so at what point do you know you can plug in this log p of x bits to be able to get out that a of j? Because it could be that 0010 just hasn't been reached yet, so I have to give a bigger index at that point of time, because maybe I have to give the 6-bit one, and at that point this bound does not hold. So like,
Yeah, I think you guys are trying to come up with the program. This is also what Will like stumbling up with. He's like, yeah, but how do I know that that is the program that I should be giving to T, or the address that I should be giving to T to say, yeah, okay, you halt. But you're facing the same difficulty as trying to come up with the shortest program for a string X. No, you could say, well, how do we know X star is the shortest program? We don't know. It's just defined this way. You know, like it's my A5 or my, I think in my proof I called it AL in general, the last one that will have stabilized, the last address. I'm not coming up with a proof that this will be, you know, your final thing, but the only thing you need is that there exists a program, namely AL, for the Turing machine T to compute X, and that the length of AL is roughly log P of X minus log P of X. I agree. You're like, yeah, but I would like to be able to code AL, or no, well, you're not able to code X star either. So it exists. But Aditya, you named the fact that, yeah, this computation runs for very long. It will. In some cases, it will be extremely, extremely long. You will meet the busy beaver function in problem sheet number 4. You will see that the busy beaver function arrives all the time. Oh, in fact, I spoiled myself. I told you not to read beyond a certain point, and then I forget what I said. Because in question A of question 5, I asked you to write down the function that grows to infinity as fast as you can think of. You've never heard what I said about this funny animal name in a function. Okay, great. There was another subtlety with this proof that I'd like to address before the break, and then after the break we're gonna, turn the page, and even that subtlety I won't do the proof, but I'll claim what's needed. The domain of T is a prefix-free set of strings. Is by construction a prefix-free set of strings. Right? Its domain is all the A's, all the possible A's, but every time we allocated an A, we cut the branches of the tree, so we were fine. But is T a self-delimiting Turing machine? And the concern is that, we had, once we had a model for all self-delimiting Turing machines, we had U, which was also a self-delimiting Turing machine, which could simulate any other self-delimiting Turing machine, and blah, blah, blah. And then we ask you to simulate T. It is clear that T's domain of definition is a prefix-free set of strings, but is it a self-delimiting Turing machine? Can it be made in a way that it only looks from left to right its input? Just to connect those two concepts, well, I really insisted on self-delimiting Turing machines, and it was one of the basic properties of a self-delimiting Turing machine is that its domain of definition then is going to be a prefix-free set of strings. Now we sort of have the converse. We have that the domain of definition of T is by construction prefix-free, but it's not that clear that it's self-delimiting. Like, if you tell me, in that example, run T on input 0, 0, 1, 0, I'm sort of happy to know that, okay, it's over. And so whenever we allocate a node, I don't exactly know how I would be able to do that in a self-delimiting way. But yeah, fortunately there's a proposition that saves us here. I'm going to state the proposition without proof, but for this course, if I want to move forward, I'll leave some supplementary notes so that you have like the proofs of all the stuff I claim and I don't take time to prove, so that we can get to a nice ending point for the course. Let Y proposition let y be some auxiliary string let t prefix be a Turing machine. Whose domain namely the set of A's such that t prefix on input AY, y is like the auxiliary string, it's sitting on the other tape. The set of A's such that this halts, whose domain is a prefix free set. Then there exists a self-delimiting Turing machine self-delimiting Turing machine TSD such that, well, they have the exact same functional behavior. TSD of whatever is the input y is identically equal to t prefix of whatever is the input y. So if this is undefined, well, this will be undefined. If this is defined with some value z, but also the left-hand side will be defined with the same value. And so that via this result, we have a Turing machine whose domain of definition is a prefix-free set. A self-delimiting Turing machine can simulate its computation and do it. Actually, by the way, some authors will prefer to view. I sort of adopted a model of computation to define the prefix complexity that is, in hand with the Turing machine. So I use the model of self-delimiting Turing machines that you can only move the reading head from left to right. If we want to take a more abstract stance on this theory, we could work with just prefix Turing machines. And it's namely all those whose domain of definition form a prefix-free set of strings. But by this result, it's all equivalent. So it doesn't matter which way to think. It's just that for that proof, what we have is a prefix Turing machine. So it's good to know that a self-delimiting Turing machine can simulate it. Yes, I'll leave the proof in the notes so we can take a break and get faster to. There's one last topic I want to discuss, and it's the topic which gets us to proving the chain rule at O of 1. And it's the topic of the existence of upper semi-computable semi-measures. Lower semi-computable semi-measures, sorry. But let's have a break now, and let's reconvene at 20 past. So, short break. All right. The coding theorem is quite curious in that, if you remember with the Shannon setting, log of 1 over p of x the ceiling of that was the length of the code words in a Shannon-Fano code. If we had a distribution p of x, we said, we were wanting to give very long code words to rare events. So and then we round it up to the next power of 2, basically. And you've worked that out in problem sheet number 1. So I think at some point I mentioned that this was sort of the self-information or the surprise in the probabilistic setting. And then the entropy, Shannon entropy, was the expectation of the surprise or the self-information. Now, I think it's quite curious that in the algorithmic setting, log of 1 over p of x is just as good a complexity measure as k of x. Just as good because they differ by a constant. Just as good because if we come up with a different universal prefix self-delimiting Turing machine, then we're just going to get another constant. So being close to the constant is as best as we can do. And so it sort of reflects this idea of self-information, but without having to refer to any distribution on which p of x is given. Because this p of x here, that's the p of x in the algorithmic setting, I said, yeah, we can think of it as a monkey in form of a typewriter, but it's just a measure over all strings. You sum over all strings, 2 to the minus the length of the program that generated. P such that u of p equals x, 2 to the minus length of p. Yeah, it may have a probabilistic interpretation if we put a monkey in front of a computer, but it doesn't need to. It could also be thought of as a measure over the strings. So that's the coding theorem we get from now, and I think it's a cool tool if we think about that, but it's a much more practical and important tool if we investigate lower semi-computable semi-measures. Lower semi-computable semi-measures. LSS for short. We're basically going to define all the stuff in lower semi-computable semi-measure. First, a discrete semi-measure is a map mu from natural numbers or bit strings, however you feel, to the real numbers, such that the sum over all x's is smaller or equal to 1. That is the definition of a discrete semi-measure. So the discrete part refers to the fact that we map from the integers to the real numbers. Okay, so it's a measure over a discrete set, namely the set of natural numbers. The fact that it's a semi-measure refers to the fact that we have an inequality here. It would be a measure in case of equality. If this would be an equality. So semi-measure just means you're close to summing to 1, but you're not really summing to 1. Actually, I say you're close. There's no notion of being close. It's just you're smaller or equal to 1. And oh yeah, all these numbers are larger than 0.
Yeah. So then it's basically just a subnormalized measure.
Yes.
Like you could just normalize this. And
We
then
could
make it
normalize
to 1.
this.
Yeah.
Correct. Exactly. We could normalize it. But the reason why we leave it unnormalized is that we want to keep it semi-computable, which will be the next point. The measure, the semi-measure, is lower semi-computable I dropped the hyphen, I think. Lower semi-computable if there exists a partial computable function mu tilde of x and t, so now it takes another parameter t, such that mu tilde of x and t is larger or equal to mu tilde of x and t minus 1, and the limit in t goes to infinity of mu tilde of x and t converges to mu of x. In the problem sheet number 3, we met lower semi-computability by above. I think to make your life a little easier, I ask you to come up with a never-ending algorithm which come up with always better upper bounds because we were computing from above. You guys needed to show that the function k of x was upper semi-computable. Most of you got it right. So you run all programs, good old trick. Whenever you find some program that halt and produce some y, then you have a first upper bound on k of y because you found some program that produces y, so the length of that program is an upper bound on the minimal length of a way to produce y. Now, how does this relate to this? Well, think of t as time. You know, if you run this never-ending algorithm for t steps, you might have found, I don't know, 16 ever better upper bounds of k of y. And as t goes to infinity, eventually you'll converge to k of y. So that's the idea here. Think of t as, t is the parameter which is going to infinity and it's going to approximate mu of x. And now this condition here says that you're always, now we're lower semi-computing, so we're finding ever better lower bounds. So this quantity here is larger or equal than the previous proxy we had for mu of x. Mu tilde of x is the proxy, the best tentative lower bound. Okay, so that's what it is to be a lower semi-computable semi-measure. Questions?
Okay, partial computable functions are allowed to have elements of the domain that map to the special symbol, the like undefined symbol or whatever.
Exactly.
It's supposed to mean non-halting programs usually. Does it have a value? For example, what if I have mu of x and some t, like, you know, I'm computing like 1, 2, 3 or whatever for t, and then one of them for the same x, but like t equals 3, suddenly is undefined or loops forever for whatever reason. Then is it allowed to go back down to a finite value? Because we didn't assign like a numerical value to that undefined thing. Basically, can I have parts of my sequence that jump off to undefined, or?
You can, or you can circumvent the problem by, you know, always keeping mu tilde a finite number. And if you want to do that, then maybe you reach with the idea of wanting to find an initial value for mu. In the case of lower semi-computable semi-measure, it's quite easy because we will, you know, you can set all of these equal to 0. Mu of x is equal to 0 for all t. Well, not for all. Also. Mu of x 0, when t equals 0, is equal to 0 for all x. And then we start and we find better upper bounds. Some of you ask me, what about that problem? Should we start with some upper bound for k of x? And the fact that I leave the possibility for mu tilde to be a partial computable function, it means that you could leave the initial value undefined, and for the first time it's defined, then you jump to a finite value. And then I think what you ask is, can I go from a finite value to my next proxy being undefined? I wouldn't know why you would want to do that.
Well, because in general, all we said is partial computable functions can map to this undefined symbol.
Yeah.
So I'm thinking of weird cases.
Yeah.
Like normally I would want to think of that a given x will just always loop no matter how many computational steps you use. But a stranger case would be an x that for some number of computational steps has a finite value of this measure, and then for others has the undefined measure. And then I'm not sure what this condition means. Like, is it allowed to jump up and down? I say up, but we didn't define like a numerical value for that symbol.
Yeah. I don't know. I don't think it's an important issue for that.
Okay, so we're always, if it's...
You can always get mu to be a finite value. It's clear for lower semi-computable semi-measures because you set it to 0 initially, and whenever you find a better bound, you upgrade it. And undefined is not a value, it's not a bound, it's not a number. So you ignore those. Because you're worried about the fact that it's partial computable, you're worried about this might be undefined.
Yeah, basically I don't know what that inequality means for the cases where it's undefined. But we don't care about them.
No, not that I can think of. Yeah.
For this case, we could even let it be total computable.
I think, yeah, in this case we could let it be total computable. Yeah. Because I don't see the problem in setting mu of x to 0 for all x except Okay, let's move on. I don't think it's an important issue, but maybe the gist of the idea of having partial computable function is that a priori, there could be some mu of x undefined. But I said it's a map from mu, from n to r. In any case we're going to use it, it's going to be a defined map. Like each x is going to have a value, so it boils down to be total in that case. Okay, let's move on and see. Maybe we see better thoughts as we move forward. Okay. The semi-measure m is universal with respect to a class C of semi-measures if it is in that class, M is in C, and it is larger than any other. Namely, if there exists a constant Whoa, that can't be true. That cannot be true. Namely, if for all mu there exists a constant C. Such that mu of x is smaller or equal to C m of x for all x. Okay, that's a definition again, so I should use my green pen. Is universal. It's universal with respect to a class, but I'm just going to highlight universal. If it is in that class, and this equation holds, so for all mu, there will be a constant such that this quantity eventually dominates up to a constant, the function mu of x. Think and apply this definition to computable semi-measures. So maybe as a sort of informal conversation, think of if C would be the class of computable semi-measures. For instance, I'm going to map x. We can come up with some mu's, right? Our favorite mu's. From n to r, I'm going to map x to 1 over x squared. Okay, it's lower semi-computable, but it's even stronger. That function here is computable. So it's a computable semi-measure. Why? Because let's sum them all. If I sum over all if I sum, so what's this name? Let me call it nu. If I sum over all x, 1 over x squared, I get pi squared over 6. So what can I do here? I could do 6 over pi squared. So I would get 1. If I sum nu of x, I would get 1. I basically normalized it. And then you can come up with any converging series that is computable and normalize it, and then make a measure or a semi-measure out of it. If you normalize it tightly, like I've done, you're going to make a measure. If you normalize it, quote unquote, by a constant which is large enough, you're going to make a semi-measure, because you're going to bring that number to smaller than 1. Like another one, mu prime will be n to r, and I map x to 2 to the minus x. Since the sum of 2 to the minus x from 1 to infinity is 1, it's already normalized. So sum of a nu prime x is already 1. We're good. Okay, what does it mean to this relation of domination? Well, it has to do with the speed at which it converges. So in this case, nu dominates nu prime. Because let's see with the definition here, there exists a constant c such that I said what? Yeah. Nu prime of x is smaller or equal to c times nu of x. I'll have to deploy these things, but it means that 2 to the minus x is smaller or equal than some constant c times 1 over x squared, which is x to the minus 2. Okay, I absorbed the normalization into the existence of that c. Now, for computable functions, it can be shown that there exists no universal semi-measure. because whatever is the computable way, you will, because then we can do better, right? You can find, so basically, this function u prime converges very fast, and therefore it's going to be quite small in this hierarchy of domination of functions. This one converges slower. But then you might know that the function x to the power of p converges for all p larger than 1. So if you take p equals 1.5, well, this function is going to dominate that one. And I think that in last problem sheet, we played with some crazy functions which were diverging or converging super slowly, right? The function, what was it?
Log, that one?
Yeah, sum over all x of 1 over x,
Log x.
log x, happen to diverge by the integral criterion. But if we would have put a square here, it converges. We have to verify, but it does. And so that defines a semi-measure, which is going to be larger than all the previous ones that I've written down so far. But can I find like a computable semi-measure which dominates them all? It's a theorem that the answer is no, not for computable semi-measures. Great. Let me now move on to semi-measures and semi-computable semi-measures, in fact.
Okay, so the universal one, okay, so you said it doesn't exist for computable functions, but for semi-computable functions it is going to, and the universal one, or any universal one, is going to grow faster than anybody else, which means it's going to converge faster.
A would be slower.
Going to converge slower. Okay.
Okay, so the example with what I wrote down here, I'm going to run out of letters, but let me call it, mu prime prime of x is equal to 1 over x log x log x squared. Now, this thing, sum over mu prime prime of x, converges. And it will converge very, very slow, so that if you try and draw like the points of mu prime prime of x as a function of x, discrete points, it's going to have to go to 0, obviously, because it converges. But it's going to dominate all the other ones that I've written. So if this is the green one, and if this is the red one, that would be like a geometric intuition for what I mean by the dominance. Oh, and yeah, for example, this would be the to be more precise, this would be my green. No. This would be my green. No. Let me think. Yeah, this would be my green. This would be my red. If you plot these points, 2 to the minus x, they're really going to go quickly to 0. If you plot these points, 1 over x squared, they're going to go to 0, but still going to remain larger than those. And the blue one is going to dominate again. So that the relationship is, for example, given by these relations. Because I also allow myself for a constant c. Okay. Proposition. I'm gonna state the main proposition and then we'll see how I want to manage time to go into the details of the explanations and the proofs. P of x, which we've already met, was defined as the sum over all p such that u of p equals x, 2 to the minus length of p, is a universal lower semi-computable semi-measure, LSS. So I think from that it's implicit that it's universal in which class? Well, in the class of lower semi-computable semi-measures, right? Because I said that to be universal, it's with respect to a class. It needs to be in that class. You guys should know by now that this is a lower well, you should know by now, we can rethink it slowly, but this is a lower semi-computable semi-measure. It's a semi-measure because the sum over all x of p of x is equal to omega, a number smaller than 1. And it's lower semi-computable because we're used to it. In the proof of the coding theorem, we were, lower semi-computing all those p of x. You're running all programs. When you find a program that halts and produces x, you add 2 to the minus length of that program, and you're coming by below to a computation of p of x. So p of x is clearly in the class of lower semi-computable semi-measures. Now it's a universal one. So what does it mean if we get those two together? So if you come up with some mu of x is a LSS. You come up with some function. Well, by the way, all of these are. They're computable semi-measures, so they are also lower semi-computable semi-measures. All of those that I've written down. Well then, if mu is a lower semi-computable semi-measure, then there exists a constant c such that mu of x is smaller or equal than c times p of x for all x. So to connect back with those, no, I should not go again here. I want to move forward. But this one dominates all the semi-measures. I will end up proving this one. I think it's quite enlightening and not so hard. But I will need another statement which I will not prove. But again, I'll give either in my lecture notes that are now available, or I'll email them to you as supplementary notes for this course, because I want to get to the final destination. Definition. Pt of x. Why not? Right? We had this definition for the universal Turing machine. Why not having the Pt for some Turing machine t defined as the sum over all p's such that t of p equals x, 2 to the minus length of p. Okay, so for some Turing machine t, in fact to each Turing machine t, self-delimiting Turing machine t, this quantity is well defined and it gives a lower semi-computable semi-measure. Okay, I should add. So that's a definition now. The mapping that goes from N to R, which sends X to PT of X, is a LSS. Okay, why is it a semi-measure? Because if we sum for all x, we're summing for all x, we're summing for all p's, so we're summing for all possible elements of the domain of t, 2 to the minus the length of that element of the domain. But t is a self-delimiting Turing machine, his domain is a prefix-free set of strings, so by Kraft inequality, once more, we have that sum would be smaller than 1. So it's a semi-measure by Kraft inequality. And why is it lower semi-computable? Well, same trick as before, right? Same trick as why I argued that this is a lower semi-computable semi-measure, because we can run over all in a dovetail fashion, calculate t of p for increasing length of p, for increasing number of steps. Whenever we find some p that halt and produce x, we add this. So it's the same argument, but with the Turing machine t instead of the Turing machine u. I explained why I wrote that down. Now the proposition, which is not so trivial, let mu be a LSS. Then there exists a self-delimiting Turing machine T such that for all x, mu of x is equal to pt of x. Okay. We define PT in a super analogous way as we define the universe. Well, we define P for the universal self-delimiting Turing machine. We argue that it is a lower semi-computable semi-measure. Now, the proposition states that, well, any lower semi-computable semi-measure can be understood as if it comes from a PT, basically. Because the statement is, take some lower semi-computable semi-measure, mu. We don't know how it's defined a priori, but it fulfills the axioms of being a lower semi-computable semi-measure. Well, then there exists a machine T such that mu of x is equal to pt of x. It's actually a cute proof, but I can't. It's okay. I have to make peace with the fact that today I really wanted to get you to the idea that, yes, to some endpoint, which I'm not going to spoil and not going to try to explain before I explain it. So I have to make peace with the fact that there are propositions that are not proven today. But like I did before, you'll receive an email for the curious ones who are like, hang on, how does that work? Accepting this proposition, we can somewhat easily prove that one, though. what's in the cloud is just restating. It suffices to show that P of x, which by the way is the same as if I had written Pu of x, right? Because I'm just trying to connect with this definition here with Pt, dominates all Pt of x. And we invoke the universality of U by the universality of U there is a program R such that U of RQ is equal to TQ. In fact, by our definition, R was a self-delimiting encoding of the Gödel number of the Turing machine I, of the Turing machine T. Sorry. Thus, Pt of x, we want to show that it's smaller than some constant times P of x. Well, it's equal to, that's just by definition, sum over all q such that T of q equals x, 2 to the minus length of q. It's my definition of Pt of x. But I'll just add 2 to the length of r, 2 to the minus length of r here. I'm adding 1. What's that? 2 to the length of r, sum over all q, such that, okay, if T of q computes x, T on input q compute x, it means that U on input RQ also compute x. Two to the minus, and then I've got the length of R, 2 to the minus length of R is going to go into that quantity. And I'm using the fact that the length of the concatenation of strings is the sum of the lengths. Okay, so I really did 2 independent steps. First, I got this term in here, and I rewrote that as that. And also, I just changed the way of understanding the sum of q's. You're not summing over all q such that T of q equals x. You're now summing over all q such that U of RQ equals x. It's the same thing. Well then, for U to produce x, doing it via RQ is one way, but it doesn't need to produce x via R something. Okay, so this quantity is smaller or equal to 2 to the length of R doesn't change. Then I'm summing over all possible ways for U to produce x, 2 to the minus length of this way. Okay, so this sum here contains more terms than it did here. It does contain the terms of the form RQ, but it contains many more terms. And we're done. So this is the sense in which P of x dominates Pt of x. there exists a fixed constant which does the job for all x. Okay, and because, by this proposition, it's claimed that any mu can be of the form pt of x, well, then we have that p of x is a universal lower semi-measure, lower semi-computable semi-measure. Now the coding theorem becomes dramatically important. Dramatics might be too much, but it's quite important. What's the coding theorem again? Maybe written in a more convenient way. We've written the coding theorem with an expression relating k of x and minus log of p of x. Let's rewrite it in an expression that involves p of x and maybe 2 to the minus k of x. Right? So the coding theorem was saying that p of x, it's obviously, this is how I started the lecture last Tuesday. It's obviously larger than 2 to the minus k of x. Right? Because p of x contains infinitely many terms, and x star is just one contribution in the sum of p of x. So 2 to the minus the length of x star is 2 to the minus k of x. But the coding theorem was that there exists a constant c such that also this holds. I actually motivated the coding theorem this way. And then we took minus the log on each side, and this c became a plus O of 1. So, can you guys spot another universal lower semi-computable semi-measure? Two to the power minus k of x. P of x is a lower semi-computable is a universal lower semi-computable semi-measure. We proved it modulo this proof, which is for you to read. And now we're like, oh, by the way, this P of x, which is super cool, it dominates all lower semi-computable semi-measure. Well, it's dominated, there exists a C such that this holds for all x. Well, it means that also this one, 2 to the minus k of x, is a universal lower semi-computable semi-measure. It's a lot of names. So the corollary of the coding theorem is probably more important than the coding theorem itself. X maps to 2 to the minus k of x is also a universal LSS. It's a corollary of the coding theorem and of that proposition. Or if we want it in the conditional case, which might be useful, x maps to 2 to the minus k of x given y is a universal lower semi-computable semi-measure given y. Given y might be useful because there might be cases as there will be one now, after I'm done explaining this, where some quantity is not exactly lower semi-computable. But oh, it would be lower semi-computable if we had y star. Oh my god, if I had y star, now this quantity would be lower semi-computable. Well then, we can apply the coding theorem in its conditional form to basically dominate the conditional version of this. So, okay, yeah, this proposition has a straightforward generalization to auxiliary information. P of x given y, which we defined last time, would be a universal lower semi-computable semi-measure given y. So yeah, it has an analog here. And I'll just have time to finish with proposition. Are there questions? I don't really need to rush. I'm still loose. I know it's a lot of stuff.
Why do we care that something is bigger or dominates this measure? What's universal about it? Like, does it have any other, advantage or like benefit that it converges slowly? Like, why do we care?
Good question. I'll move on. I think it partially answered your question. Question 6 might also be of interest. You know, we had this chat last time about omega n, the number of programs of length smaller or equal to n that halt. We know that that number is smaller than 2 to the n plus 1 because there's only so many programs. But what you're going to be able to prove in question 6 is actually much stronger. So many results of this kind are only possible with this kind of analysis. And I'm going to finish with the chain rule, which is also a corollary of this. So, yeah, why do we care? Good question. Proposition, chain rule, hard side. Oh. For all x, for all y, k of y plus k of x given y star is smaller or equal to k of xy plus O of 1. In problem sheet number 3, you showed the other way around, where I put the k of xy on the left-hand side and these two terms on the right-hand side. So this is the hard side. Right, this is equivalent to, there exists a C such that k of y plus k of x given y star smaller or equal to k of x, y plus c. That's what this O of 1 means for all x and y. The c is independent of x and y, and this holds. Okay, that's equivalent to, there exists a C such that, now I'm going to put this term on the other side and that term on the left-hand side. Minus k of x, y plus k of y smaller or equal to minus k of x given y star plus c. Very basic manipulations. And then I'm taking the exponential on each side, 2 to the power of each side, so it preserves the side of the inequality. There exists C such that 2 to the minus k of x y. I could do plus k of y here. I could multiply by 2 to the k of y, but I'm going to divide by 2 to the minus k of y instead. Is smaller or equal to 2 to the c times 2 to the minus k of x given y star. Okay, so that's the hard side of the chain rule. I've just remanipulated it briefly. Buena suerte. Buena. How do we prove that? This will be our universal lower semi-computable semi-measure. So we just need to show that this quantity here is a lower semi-computable semi-measure, given y star. Because here you allow yourself to have y star. This is like a conditional version, given y, where here we have given y star, because we give y star as a resource. And you're like, oh, how wonderful it is that I have y star, because y star will enable you to not care about the denominator, because since you have y star, 2 to the minus k of y is easily computable, and you can show that this quantity here is indeed a semi-measure, a lower semi-computable semi-measure, given y star. That's what you're done. You proved it. We proved the hard side of the coding theorem this way. Yeah, I was hoping to do it, the proof. I had too many hopes for today. In fact, my largest hope is, I really want to thank you. Thank you all for this course. It was I'm emotional. It's great. I loved it. I truly loved it. No one asked me. In fact, Stefan, I actually want to thank Stefan, by the way, for proposing to me that I could do this course, and also for actually defending it at the assembly and all the paperwork he did with the university for me to give this course. I thank him, and I want to thank you. As I said, you were a large motivation for me to wake up on Tuesdays and Thursdays and prepare this course and try to make it look good and understandable. And all your smiles and your interactions was yeah, thanks a lot.
Thank you.
I learned a lot. Good luck in your projects. If you like research, I hope you're going to have fun doing it. Like question 3. And yeah, let's keep in touch. I would be really happy to exchange emails with all of you in 3 or 5 years from now, whatever life takes us. Let's have drinks if you guys want. And yeah, we can also have questions if you have questions or comments. Thank you.